So today we're going to look at rational functions, and we're going to look at vertical asymptotes and holes, also called removable discontinuities, but we will refer to them this year as holes. So for each of these problems, we'll find the domain, simplify the expression, and then find the domain of the new function. And we will call the new function f sub 1 of x. So just to remember, this will be called f sub 1 of x. So here, the domain of f is simply x such that x cannot be 0. Or, if you remember, I can write that as the real numbers without 0. If I simplify this, nothing happens. Stays the same. So the new domain will still be the real numbers without 0. Here we have g of x, which we can write as x plus 2, x minus 2 by factoring. And then when we do that, the domain of g is equal to all real numbers except for -2 and 2. So if we simplify g1 of x, nothing cancels, so we are still left with x plus 2, x minus 2. So the domain of g1 is the same thing as the domain of g, everything but 2 and -2. Okay, now we have h of x, which is 3 times x minus 2, and here in the denominator we factor the difference of 2 squares. And now you'll note that this is going to have some cancellation, so finally our new function is going to be different than our old one. So the domain of h is the same as the domain of g. This is the set of all real numbers except for -2 and 2. And now, if we simplify, the x minus 2's cancel, and thus we are left with the domain of h of 1 being all real numbers except for -2. And now, just a note, the new function h sub 1 is not equal to h of x. In order for two functions to be equal, their domains have to be equal. And as you note, the domain of the original function and a new function are not equal. So these functions are not equal. They might simplify to each other, but remember, we can only do this cancellation if x is not 2. If x is 2, this original function is undefined, but if x is 2, this new function is 3/4. So these two functions are not equal because of that one value of x. It produces two completely different results. Here, if we factor, and we're factoring just to check for later when we simplify, we'll notice the x plus 3's cancel. Okay, oops, sorry. The domain of m is equal to all real numbers except for 0, 2, and -3. That's where the denominator is 0. And then if I simplify, the x plus 3's cancel, and I'm left with a new function that's not equal to the original. And the domain of this is all real numbers except for 0 and 2. Okay, we'll come back to this in a moment. We're going to need it. Next, here we have p, and it's already simplified, or rather factored for us, so it'll be easy to simplify. The domain of p is all real numbers except for 0, -1, 3, and -6. And then if I find this new function after canceling, the x's cancel, the x's plus 1 cancel, and I'm left with this function, whose domain is different than the original, so it is not equal to the original function. Note that this new function has 2 additional elements in it, in its domain, than the original did. So here we have 0 and -1 in the domain, here they are not. In problem number 6, the domain is all real numbers except for 0 and 1/3. And then if we simplify this, the 3x minus 1's cancel, and the new function has a domain of all real numbers except for 0. In problem number 7, this is the sum of 2 cubes, which we remember from our polynomial unit. Can factor that way. And if you didn't remember that, we noticed that -1 is a root up here. And if -1 is a root, then x minus -1, or x plus 1 is a factor. And then I could have simply done synthetic division, x cubed plus 1 divided by x plus 1 to get x squared minus x plus 1. So even if you don't remember the formulas, you can still always find a root, which will give you a factor, and then do division to get the other factor. And this quadratic does not factor anymore. And we note that the x plus 1s are going to cancel in a minute. The domain of the original is all real numbers except for 0 and negative 1. The new function, we have the x plus 1's canceling, x squared minus x plus 1 over 3x. So the new function, the domain of the new function, forgive me, is all real numbers except for just 0. And again, you notice that the new function, the domain is either equal to or has less elements than the original. If nothing cancels, then they're the same. If stuff cancels, then that allows the domain to have a few more elements in it. This one's kind of interesting. The domain of S is all real numbers except for 3, 2, and negative 1. And then our new function, s of 1, the x minus 3's cancel, the x minus 2's cancel, the x's plus 1 cancel, and we're left with just 5 over 4. And the domain of this new real function is all real numbers. This is a constant function, so any value of x will work. So that's kind of interesting. And then the final one, let's see. To do this, we would have to factor the top by grouping. This is x squared times x plus 1 minus 1 times x plus 1, and then the denominator is x squared minus 1. The numerator, we get an x plus 1 and then an x squared minus 1, which normally I would factor further, but then I noticed that in the denominator I also have an x squared minus 1, so those will cancel. It just makes finding the domain a little bit harder because then I have to remember that there are two elements here. The domain of this h would be all real numbers except for 0, negative 1, and 1. My new function, h sub 1 of x, would have these canceling, and I would have x plus 1 over x squared. So then the domain of the newest function would simply be all real numbers except for 0. And now if you're wondering why we're doing this, it's because this original function's domain and this new function's domain that we've defined will help us in finding vertical asymptotes and holes. See, next year we will have these things called limits that will allow us to find these values a little more unambiguously. We'll have better definitions. Your textbook does a good job of trying to explain it using the concepts of infinity and increasing and decreasing without bound, but I found that it's a lot easier to kind of go through this process because this process itself has some graphical interpretations, which you'll see. We'll explain in a second. So here's a theorem, and this is not a famous theorem or anything. It's something I came up with. Let f of x equal p of x over q of x be a rational function. That means p of x is a polynomial and q of x is a polynomial. And let f sub 1 of x equal p sub 1 of x over q sub 1 of x. And f sub 1 of x is defined as f of x after it is simplified, meaning any terms that the numerator and denominator have in common after they are completely factored will be canceled. Well, if the denominator of my new function is equal to 0 at some point a, then that means that x equals a is a vertical asymptote of the graph of f of x. So if after we simplify there are still values that make the denominator 0, then x equaling those values gives us a vertical asymptote. However, if our original function has a value of x that makes the denominator 0, but then after simplifying it no longer makes the denominator of 0, then f has a hole at the point a, comma, f1 of a. And the reason for this is because if I plug a into the original, it's undefined. But if I plug a into the new one, now all of a sudden I have a function value. What canceling does, and we'll go through it with some examples, but what canceling does is it kind of fills in the hole. So here's just an example to look at. Let's look at the example f of x equals x squared. We'll do we'll do that. X squared minus 1 over x minus 1. So the domain of the original function is all real numbers except for 1. So what does that mean? That means if we try to plug in 1, this is undefined. However, if I try and find this simplified function, we know that the numerator simplifies into x plus 1 times x minus 1. After I cancel, I just get this linear function. And the domain of this linear function is all real numbers. So what happened there? Well, our value of a here is 1. 1, let the original denominator be 0, but the new denominator, which is just 1, is not 0. That means that this function, so f has a hole at x equals 1. And here's the interesting thing. If we graph this function, as weird as it looks, this function actually comes out to look like a line with slope 1. And you go ahead right now and just graph it in your graphing calculator. And it'll look just like a line with slope 1 and y-intercept 1. The problem, though, is that this is not defined at 1. So at 1, there has to be a hole. And sure enough, if in your calculator you go to second trace, and then you let x equal 1, you'll see that your y value is going to be completely empty. There's a hole there. You can't even see it on the calculator because it's just one little point. But it's there. And that's because the original function isn't defined there. So how do I know it's a hole and not a vertical asymptote? Well, if you remember what we did, we said, okay, let's look at this function, and to figure out if it has a hole or not, let's cancel anything that we can when we factor. Well, remember, why can we cancel this? Because x minus 1 over x minus 1 is always equal to 1. Or is it? It's only equal to 1 when x doesn't equal 1. When x equals 1, this is completely undefined. So I can't plug 1 in here. But when I cancel it out, I get rid of this problem. Now there's no longer an x minus 1 in the denominator. So when we cancel this out, what we've really done is we kind of fill in the hole. That's what canceling does if we completely eliminate this expression. We fill in the hole. Now, interestingly, if we look at a similar function, x minus 1 over x squared minus 1, here the domain of g is everything except for negative 1 and 1. So you say to yourself, well, this is very similar to what we just did. Well, it is, but the new simplified function will be 1 over x plus 1. Our new function still has a problem. We still cannot plug in negative 1. This is not going to be a line, not even close. What's happening here is we remove the 1 as a problem. 1 is not in the domain of the original, 1 is in the domain of the new one. So this is going to have a hole at x equals 1. And specifically, the y-coordinate of the hole will be what the y value is in the new function. Because when we fill in the hole, that's what we do when we cancel. This will give us what the y value is. So when x is 1, this is the point 1, 1/2. And similarly up here, this would be the point 1, 2, because when I plug in 1, I get 2. So you ask yourself, well, what about the negative 1? Well, the negative 1 we couldn't cancel. The negative 1 is a problem. Even if we could cancel it, when all was said and done, it's still a problem in our final simplified function. So we couldn't fill in the hole. We couldn't cancel it. We couldn't fill in the hole, which means that g has a vertical asymptote x equals negative 1. And sure enough, if you look at a graph of this thing, whoops, let me do a graph here, at the point 1, 1/2, there's going to be a hole. At the point negative 1, there is going to be a vertical asymptote. And this is point 1. I'm going to show you what this looks like if you graph it on your calculator. It comes here and it looks like this. And then if I go all the way to the left, it's going to look something like this. And this is something we're going to be doing a little bit in a lesson in the future. We're going to be learning how to graph these things. But for now, it's important that you're able to find holes and vertical asymptotes. So, for example, in these problems that we did, in this first one, the original domain had an x value where it was undefined of 0. So there's either going to be a hole or a vertical asymptote at 0. I check the simplified function, 0 is still a problem. So this has a vertical asymptote at x equals 0. Problem number 2, -2 and 2 were problems in the original. They are also problems in the final. So this is going to have vertical asymptotes at x equals -2 and at x equals 2. Problem number 3, a little bit different. Here we were able to cancel something. So in the original, -2 and 2 were a problem. In the final, only -2 is a problem. So my vertical asymptotes are where the rational function is undefined in its simplified form, x equals -2. And then the whole will be where it was undefined, but we were able to fill it in. In this case, it's at the x coordinate of 2. And then to get the y coordinate, I use the simplified function 3/4. And again, I can't use the original function, because if I plug 2 in here, I get undefined. And I can't have a hole at position 2, undefined, because I don't know how to graph undefined. Problem number 4, also very similar. Here we go. 0, 2, and -3 are where the original is undefined. Here, 0 and 2 is where it's still undefined. So we have vertical asymptotes at x equals 0 and x equals 2. And then we have a hole at the point -3. And then I plug it in here and I get -6 over, yuck, -3 times -5 is +15. And again, it didn't say to simplify, so I'm not going to. Problem number 5, we'll have vertical asymptotes at x equals 3 and x equals -6. And we'll have not horizontal asymptotes, I'm sorry. And we'll have holes at the point, well, we were able to plug in 0. So 0, comma, and when I plug 0 in here, I get -18 over -18, that's 1. And at the point -1, comma, when I plug in -1, I get -7 times 2, that's -14. And in the denominator, I get 6 minus 1 is 5. 5 times -4 is -20. So this will be a plus, because they're both negative. And that's the same thing as 7/10. Here, my vertical asymptote will only be at the point x equals 0. And my hole will be at the point when x is 1/3 and then y is 3. Here, there is a vertical asymptote at x equals 0 and a hole at the point -1, comma, let's see, 1, 2, 3 over -3 is -1. That's kind of cool if I did the arithmetic right. Here, I was able to cancel out everything. So vertical asymptotes, none. But the holes then, since I could cancel everything out, would be at 3, 5/4 and 2, 5/4 and -1, 5/4. In fact, if we were to actually graph this function, here's -1, here's 2, here's 3. This function is just y equals 5/4, except with holes at those 3 x values. If you want to try graphing this in the calculator, go ahead and you'll see it's just a horizontal line with 3 holes. And then finally, in problem number 9, we have a vertical asymptote at x equals 0, because there's a problem there. And our hole is at -1, and there's another hole at 1. And then to find the y values, I just plug that in. Well, at -1, this is 0. And at 1, this is 2. And there you have it. One thing that you need to realize is the following. Just because you cancel doesn't mean your function has a hole. So just as an example of that, let's say that h of x is 3, x minus 1 squared, x plus 2 cubed, x minus 3 squared over, let's say, 5, x minus 1, x plus 2 to the 4th, and x minus 3 squared. So obviously the domain of h, since I've already have it factored, is everything except for 1, -2, and 3. And then when I simplify this, and I purposely did it this way, the numerator still has the 3, the denominator still has the 5. The x minus 1's cancel, so that's nice. The x plus 2's cancel. And then here, the x minus 3's all cancel, so I'm just left with this. So note what canceled here. I canceled every single term. And yet, even though I canceled all the terms, I'm still going to wind up with a domain that is not all real numbers. So I'm still going to have an asymptote and not a whole. So my vertical asymptote here will be at x equals -2, even though I canceled this. The problem is, yeah, I was able to cancel it, but I couldn't cancel it enough to completely fill in the hole, which means it's not a hole. There was still a problem left there. The holes will be where x is 1 and where x is 3. And I really don't know what those values are. We can try it. Let's see, when x is 1, well, that's 0, so that's nice. And when x is 3, this is 6 over 25. And that is what you need to know about vertical asymptotes and holes. I hope that this has helped. Now you can do the work, and just so you know that I am okay with this, this video gets my Cetron seal of approval. Hi, everybody.